Hey everyone! In this video, we're going to learn about Newton's second law and free body diagrams in 2 dimensions. As we'll learn throughout this unit, most scenarios involve more forces than the ones that we're applying to it. On Earth, this includes gravitational, normal, and friction forces. And objects usually move in either the horizontal or the vertical direction, but not both. So to really understand how Newton's second law works in 2 dimensions, let's imagine we're deep in outer space, just like the video on Newton's first law. Out here, an object can float around on its own, without touching other objects or surfaces, so we can assume there's no normal forces or friction forces on the object. We're also going to assume there's no gravitational forces, and there's no forces from air resistance. Then we can apply our own forces and see how the object moves. So let's say we have a box with a mass of m and 4 forces acting on it in different directions. It doesn't matter what's causing the forces. Maybe the box is being pulled by 4 rocket thrusters, but we're just given these forces. And we're going to start by using variables first, and we'll use numbers later. So how do we apply Newton's second law to this box? What would be the net force and the acceleration? We might think about adding the magnitudes of all the forces together to get the net force. But we can't actually do that in 2 dimensions. We can only add or subtract the values of the forces along the same axis or the same line. So we can add forces 1 and 3 together because they're both in the horizontal direction. And separately, we can add forces 2 and 4 together because they're both in the vertical direction. But we can't add forces 1 and 3 with forces 2 and 4. So what do? Well, we just focus on each direction separately, and we write Newton's second law for each one. Let's look at the horizontal direction. Newton's second law says that the net force in the horizontal direction is equal to the mass times the acceleration in the horizontal direction. This is basically what we did in the last video, where we only focused on 1 dimension. Even though we don't know the values of forces 1 and 3, they're going to result in some net force to the left or the right, which will cause the box to accelerate in that direction, or it won't accelerate if the forces cancel out. And then we can do the same thing for the vertical axis. Forces 2 and 4 will result in a net force, up or down, which will cause the box to accelerate in that direction. Instead of calling these the horizontal axis and the vertical axis, we're going to call them the x-axis and the y-axis, just like we did in kinematics. The x-axis is usually horizontal, and the y-axis is usually vertical. So now we can say the net force in the x direction is equal to the mass times the acceleration in the x direction. And the net force in the y direction is equal to the mass times the acceleration in the y direction. We call the x and y axes the coordinate system, and drawing the coordinate system will be the first step when solving problems. This is what determines which forces are acting in the x and y directions, and which forces are positive and negative when we calculate the net force. So this is how we're going to use Newton's second law in 2 dimensions. We're just splitting it up into 2 equations, one for the x-axis and one for the y-axis. And the mass is the same for both equations. Just like we learned when working with projectile motion, the x and y directions are independent. So the force and the acceleration in the x direction are independent from the forces and the acceleration in the y direction. The horizontal forces do not affect the vertical acceleration, and the vertical forces do not affect the horizontal acceleration. Alright, so what does this look like using these forces? Let's start with the x direction. The left side of this equation is the net force. Technically, we're always adding the forces together. But now that we established our coordinate system, F1 is pointing to the left, which is the negative x direction, so F1 is negative. F3 is pointing to the right, which is the positive x direction, so F3 is positive. So we can write the net force as negative F1 plus positive F3. The order doesn't matter, so we could write positive F3 plus negative F1. Again, we're adding the forces, but each force might be positive or negative based on its direction. You can also think of it as adding all of the positive forces to the right, and then subtracting all the negative forces to the left. But either way, this is the net force in the x direction, which is equal to the mass times the acceleration in the x direction. For the y direction, F2 is pointing up, which is the positive y direction, so F2 is positive. F4 is pointing down in the negative y direction, so F4 is negative. So the net force in the y direction is positive F2 plus negative F4. We can also write this as negative F4 plus positive F2, or just F2 minus F4. That's the net force in the y direction, which is equal to the mass times the acceleration in the y direction. And that's it. That's how we apply Newton's second law in 2 dimensions. It might seem like we haven't really done anything, because we don't have any numbers and we didn't answer any questions. But this is how we're going to start every problem that involves forces. The point of applying Newton's second law is to get to these 2 equations, which will be different for each scenario. Once we have these equations, the physics problem just becomes an algebra problem. We've turned the physical scenario into 2 equations, and we can plug in values that were given and then solve for an unknown variable. So if we were given 2 forces and the acceleration in the x direction, we could solve for the mass because it's the only unknown variable in that equation. Or if we were given 1 force, the mass, and the acceleration in the y direction, we could solve for the unknown force F4. So we don't just use Newton's second law to find a particular thing, we use it in every scenario to get those 2 equations. Then we can solve for whatever the question is asking for. So let's walk through an example using numbers. A 5 kilogram box has multiple forces acting on it, as shown below. What is the magnitude and direction of the acceleration of the box in the x direction? So, what is the value of the acceleration, and is it right or left? Pause the video and try answering this question on your own. Again, we usually say right is the positive x direction and up is the positive y direction. Based on that, the 55 Newton force is in the positive x direction, the 40 Newton force is in the negative x direction, the 20 Newton force is in the positive y direction, and the 30 Newton force is in the negative y direction. The question is asking for the acceleration in the x direction, so let's write out Newton's second law in the x direction. The left side of the equation is the net force, which would be 55 newtons minus 40 newtons. Again, you could also write this as 55 plus negative 40, or negative 40 plus 55. The right side of the equation is the mass times the acceleration in the x direction. We can plug in 5 kilograms for the mass, but we don't know the acceleration. That's what we're trying to find. Next, we can simplify the left side. 55 minus 40 would be 15 newtons. So the net force in the x direction is positive 15 newtons, which is 15 newtons to the right, because right is the positive x direction. If we divide both sides by 5 kilograms, then the acceleration is equal to 15 newtons divided by 5 kilograms, which gives us 3 meters per second squared. Remember, a newton is equal to 1 kilogram meter per second squared, and if we divide newtons by kilograms, we get meters per second squared. So that's the answer to this question. The magnitude of the acceleration in the x direction is 3 meters per second squared. Since the value we got was positive, it must be accelerating to the right, because right is the positive x direction. Now let's answer the same question, but find the acceleration in the y direction. Pause the video and see if you can solve it first. So now we want to use Newton's second law in the y direction. The net force would be 20 newtons minus 30 newtons, or we could say 20 plus negative 30, or negative 30 plus 20. We still plug in 5 kilograms for the mass, and we want to find the acceleration. The left side is 20 minus 30, which is negative 10. So the net force in the y direction is negative 10 newtons, which is 10 newtons downwards because down is the negative y direction. If we divide both sides by 5 kilograms, then the acceleration is negative 10 newtons divided by 5 kilograms, which is negative 2 meters per second squared. So the magnitude, or the absolute value, of the acceleration in the y direction is 2 meters per second squared, and its direction is downwards. So we have a 5 kilogram box with these forces acting on it. We just found the net force and the acceleration in the x and y directions. But how is this box actually going to move? Will it accelerate to the right, or will it accelerate down? Well, it'll do both. What we just found are the components of the actual acceleration vector. So now let's answer this question. What is the magnitude and the direction of the acceleration of the box? If we found the components, what is the actual acceleration vector? Pause the video and see if you can figure it out. We learned in kinematics that we can combine the x and y components to form a right triangle where the vector is the hypotenuse. So if these are the x and y components of the acceleration, then the actual acceleration vector looks like this. And we can find the magnitude of the vector by using the Pythagorean theorem. If we plug in the values of the x and y components, which are the two legs of the triangle, we get 3.6 meters per second squared for the acceleration of the box. And the acceleration is in the direction of this vector. Since we had already found the x and y components of the acceleration, that method was faster. But we could have also combined the x and y components of the net force to find the actual net force vector. If we do that, we get 18 newtons for the magnitude of the actual net force. So we have 4 forces acting on this box, and the net force vector is 18 newtons in this direction. Now that we have the magnitude of the net force vector, we can just use Newton's second law to find the acceleration vector. If we plug in 18 newtons for the net force and 5 kilograms for the mass, we get 3.6 meters per second squared for the magnitude of the acceleration. That's the same value we got before. And Newton's second law says that the acceleration is in the same direction as the net force. So this is really what would happen if an object is free to move in any direction. There are multiple forces acting on the box, and the net force is 18 newtons in this direction. So the box accelerates at 3.6 meters per second squared in that direction. In most scenarios, an object only moves in the x direction or the y direction, so we don't usually combine them to find the actual net force or acceleration vectors. But that's how Newton's second law works in 2 dimensions. If most objects experience forces in the x and y directions, why would they only move in one direction? Here's a few quick examples. This box has 4 forces acting on it. The net force in the x direction is 2 newtons to the right, 8 newtons minus 6 newtons. But the 2 forces in the y direction have the same magnitude and act in opposite directions, so the net force in the y direction is 0, and we can say the forces are balanced in the y direction. This means that the box will accelerate horizontally, but it won't accelerate up or down, even though there are 2 forces in the y direction. This happens all the time when an object moves along the ground or some other horizontal surface. For this next box, the net force in the y direction is 5 newtons upwards, 7 newtons minus 2 newtons. But the forces in the x direction cancel out. There's no net force in the horizontal direction. Those 2 forces are balanced. This means that the box will accelerate upwards, but it won't accelerate left or right. For this last box, the forces are balanced in the x direction and the y direction. They each cancel out, and there's no net force in either direction. So this box doesn't accelerate at all, even though it has 4 forces acting on it. This is what's happening with most objects that are sitting at rest. There's usually friction or other forces involved that are balanced in each direction. So now that we've covered the basics, let's walk through 2 more examples. Here's a 10 kilogram box with multiple forces acting in each direction. What are the x and y components of the acceleration? Pause the video and try to solve it first. We're using the same coordinate system, so these forces are in the positive x direction, these are in the negative x direction, these are in the positive y direction, and these are in the negative y direction. Let's start by finding the acceleration in the x direction using Newton's second law. To get the net force, we would add positive 7 newtons, positive 6 newtons, negative 8 newtons, and negative 9 newtons. So we're adding 2 positive forces and 2 negative forces. We can also write this as 7 newtons plus 6 newtons minus 8 newtons minus 9 newtons. This is the same thing, but you can think of it as adding together positive forces and subtracting any negative forces. Then we can plug in 10 kilograms for the mass, and we're trying to find the acceleration. The net force simplifies to negative 4 newtons, which means the net force in the x direction is 4 newtons to the left. If we divide negative 4 newtons by 10 kilograms, we get negative 0.4 meters per second squared for the acceleration in the x direction, which is 0.4 meters per second squared to the left. Now let's use Newton's second law in the y direction. The net force would be 2 newtons plus 13 newtons minus 7 newtons minus 3 newtons. Again, we plug in 10 kilograms for the mass. The net force simplifies to positive 5 newtons, which means the net force in the y direction is 5 newtons upwards. Then we divide 5 newtons by 10 kilograms, and we get positive 0.5 meters per second squared. So the acceleration in the y direction is 0.5 meters per second squared upwards. So that's what it looks like when we add multiple forces in each direction. Now let's look at one more example. Here we have a 2 kilogram box with 3 forces acting on it, but the 10 Newton force is at an angle. So how would we find the x and y components of the acceleration? So we're still going to use the same coordinate system, which means the 6 Newton force is in the negative x direction, and the 3 Newton force is in the negative y direction. But what's the direction of the 10 Newton force? Is it pointing in the x direction or the y direction? Well, it's kind of pointing in both directions. It's pointing to the right, and it's pointing up. So we have to include it somehow in both equations. Whenever we have a force at an angle, and it's not parallel to the x-axis or the y-axis, we need to find the x and y components of that force. The x component is parallel to the x-axis, and it would point to the right because the 10 Newton force points to the right. The y component is parallel to the y-axis, and it points up because the 10 Newton force is pointing up. Remember, a vector and its 2 components form a right triangle, so we can use the trig functions and this angle to find the components. People like to try and memorize whether sine or cosine goes with the x or y components, but that depends on which angle is given. It's better to remember that sine is used for the component that's opposite from the angle, and cosine is used for the component that's adjacent or next to the angle. In this case, the x component is next to the angle, so cosine of 30 degrees is equal to the adjacent side, the x component, divided by the hypotenuse, which is the magnitude of the vector, 10 newtons. If we rearrange that, we get 8.66 newtons for the adjacent side of the triangle, which is the x component of the 10 Newton force. We do the same thing for the y component, but we use sine, because the y component happens to be opposite from the angle. That gives us 5 newtons for the y component. So even though this force is pulling the box with 10 newtons at this angle, we can also say that the force is pulling the box to the right with 8.66 newtons, and it's pulling upwards with 5 newtons. We can draw the components anywhere as long as they're pointing in the right direction. So if it helps, you can draw the y component so it's attached to the box. The right triangle just makes it easier to find the components using the trig functions. So now that we have the x and y components of the 10 newton force, we ignore the 10 newtons and we only use the components, and we treat them the exact same way as any other forces. So for the x direction, the net force would be 8.66 newtons minus 6 newtons, and we plug in 2 kilograms for the mass. If you want, you can also leave the x component as 10 newtons times the cosine of 30 degrees, instead of calculating it first. 8.66 minus 6 gives us positive 2.66 newtons for the net force in the x direction. If we divide that by 2 kilograms, we get positive 1.33 meters per second squared for the acceleration in the x direction. In the y direction, the net force is 5 newtons minus 3 newtons, or we can leave the y component as 10 newtons times the sine of 30 degrees. Again, we plug in 2 kilograms for the mass. The net force becomes positive 2 newtons, and that gives us 1 meter per second squared for the acceleration in the y direction. So that's how we work with Newton's second law when there's a force at an angle. We find the x and y components, and we use those instead of the original force. To wrap things up, let's do a quick review of the steps for drawing a free body diagram and applying Newton's second law. The first step is to establish the coordinate system, which is the positive and negative directions of the x and y axes. We usually say right is the positive x direction, and up is the positive y direction. The next step is to draw a free body diagram of the object with all of the forces acting on it. And like we just covered, if a force is not parallel to the x-axis or the y-axis, we need to draw and write out the x and y components of that force using the trig functions, usually sine and cosine. In the examples we did, the free body diagrams were already drawn for us. We were told what forces were acting on the object. But after we learn about the different types of forces in this unit, you'll be able to draw a free body diagram yourself for any scenario, and you'll know what forces to draw in which directions. Also, don't worry if your force vectors are not to scale when you draw them, unless the question says that they should be. Just make sure that the direction of each force is correct, and draw angled forces long enough so you can also draw the x and y components. The next step is to write out Newton's second law for the x and y directions. And the last step is to plug all of the known values into those equations and solve for the variable that you want to find. So we plug in any forces that we know, the mass, or the acceleration if it's given to us. Then the physics problem becomes an algebra problem, and we just have to solve the equations to find the value that we want. In the next lesson, we'll finally cover Newton's third law of motion. We'll learn how objects exert equal and opposite forces on each other, and we'll learn about normal forces and how they work. But that's it for this video. Thanks for watching, and I'll see you in the next one.